Let's talk about instruction pipelining. The instruction pipelining is a pure hardware technique that all modern processors use to improve performance. The idea is to divide the execution of individual instruction execution into a series of uniform and sequential steps or stages which are performed by different hardware units. Therefore, the hardware executes multiple instructions with the different part of instructions processed in parallel. This technique significantly increases the instruction throughput, which is the amount of instructions executed in a unit of time. This technique targets to improve the instruction level parallelism. Here is a 5-stage breakdown of individual instruction execution. First stage is fetch. At this stage, the hardware reads the instruction from memory. The second stage is decode. At this stage, the hardware understands the instruction and registers. The third stage is execute. This stage performs actual calculation to generate value or address. The fourth stage is memory stage. At this stage, the hardware reads or writes data from or to memory. The last stage is write back, and at this stage, the hardware writes results to registers. This is an example of simple RISC processor instruction execution steps. However, modern processors have a lot more complicated and sophisticated the instruction execution breakdowns or stages. Let's understand the instruction pipelining technique by visualizing and comparing with the case without pipelining. This is a 3-stage example, meaning each individual instruction execution breaks down into 3 steps. Unpipelined processor, top graph, executes one instruction after another in a sequential fashion. And this is what we assumed so far. So the hardware completes the one instruction before starting to execute next instruction. 3-stage pipelined processor, in contrast, executes the first stage of the first instruction, and next clock cycle it executes the second stage of the first instruction and the first stage of the second instruction. Next clock cycle, the hardware executes the third stage of the first instruction, the second stage of the second instruction, and the first stage of the third instruction. Remember that this is possible because the hardware has a separate and independent hardware units for each stage. Therefore, on 3-stage pipelined processors, up to 3 instructions are executed simultaneously. We have a real-world example of pipelined execution, car washing machine. It divides a car wash process into independent stages and keeps pushing a series of cars into the machine, and it completes car washes in a pipelined fashion. Again, this is possible because car wash process is broken down into multiple steps and the machine has independent parts to take care of each step. The same thing. In practice, the perfect instruction pipelining is challenging because each stage may take different times. In the example here, stage B takes the longest time and stage A takes the shortest time. To implement the instruction pipelining in hardware, all stages must have the same duration. So stage B determines the duration of pipeline stages. Therefore, there are idle times in stage A and stage C. It's challenging or impossible to partition instruction execution into perfectly balanced stages. Let's talk about the speed up that we can get from instruction pipelining. If we assume all stages are perfectly balanced, for example, all stages take the same time, and if we ignore relatively tiny pipeline filling time at the beginning and the exiting time at the end, the maximum speed up we can get is simply the number of stages. For example, with the 5-stage instruction pipelining, we can get 5 times speed up compared to unpipelined execution. In reality, the pipeline stages may not be perfectly balanced, so speed up may be little less. The instruction pipelining improves performance thanks to the increased instruction execution throughput. As a matter of fact, the execution time of each individual instruction execution does not decrease, but actually increase slightly due to stage imbalance and increased hardware complexity.